in collaboration with NASA and with the von Karman Institute. He has been visiting researchers at the NASA Supercomputing Division and also at the Department of Aeronautics and Astronautics at Stanford University. Among his awards, he has been Jacques Sadamar Postdoctoral Fellow at École Polytechnique de Paris. He has the silver medal in the Aircraft Taft Leonardo da Vinci Award, and he recently received the ERC Standing Grant to work on the development of high-order moment closure for plasma. And I understand this is the topic he's going to talk today. Okay, thank you.
So you can hear me. Yeah. Thank you very much. It's very special to be here. I'm born and raised in Madrid. It was sunnier when I was last time when I left. And indeed, it's not crazy to think that maybe 20 years ago we met in the corridors of Polytechnica. So yeah, I'm going to start with this topic. So my career, research career, worked on different topics, mainly on partially ionized plasmas, but applied to different fields actually. And indeed, partially ionized plasmas can be found in many scenarios. Particular in Leuven, I studied the sun chromosphere, so it's the upper layer of the atmosphere of the sun. So the part of the sun that we see is the photosphere, so it's just the layer that is above. And it's a plasma that is partially ionized, actually. In some parts, it's even ionized. And indeed, some of the models that are used here can be applied in this region also, even though it's a magnetized plasma. Okay, so, right now, I'm mostly working on electropropulsion, but there is also some partially ionized plasmas in fusion reactors. Okay, and as you know, because you also work on this, it's a very challenging regime. Because of the different species, we have different species with different masses, different charges, and they behave differently with respect to the electromagnetic field. Also, the presence of the anomalous transport that I believe Davide will talk about much more today. And also the regime where collisions are important, but is still weakly collisional. So they play a role, but fluid models still have problems, okay? So to do this talk, I had a bit the problem of not knowing too much if talking just about one thing or doing a collection of topics and just giving some ideas of each of them. So as it's a broad audience, I chose this second way of doing. So it's a bit frustrating sometimes to not understand everything, so feel free to contact me if you want. So the starting point, and I don't want to spoil for today the topic, so I will not talk too much, but my starting point was also the multi-fluid equations, okay? So multi-fluid equations consider the different species in plasmas as different fluids, right? Like are interpenetrating, and they interact among each other through collisions. So the collisions are these blue terms, but also they interact among each other by the electromagnetic fields, right? Because the charged species, they create fields also. They create current, they create charges. And also they have each of them, which is a difficult topic. Each of them, they might be out of equilibrium, and they have viscosity or heat flux, right? And there is most of the literature is true that was mainly based on the coupling with the electromagnetic fields, so the two fluid or multi-fluid in some cases and later in the last 5 years, probably, 5-6 years, even though Kagas is a bit early. Also, they studied the electrostatic case, which actually is not easier, I must admit. So just to show some pictures and some nice videos. So this is during the thesis I was studying magnetic reconnection. So for those who are maybe not familiar with these processes, in ideal MHD, in ideal magnetohydrodynamics, the magnetic field lines are tied to the plasma. So in principle, they are frozen. We use this term frozen into the plasma. And when then two antiparallel magnetic fields encounter in a very small region, they can change topology. They can reconnect. And then there is a transformation from magnetic energy into energy to the plasma, thermal and kinetic, okay? And with multi-fluid, what can we see? We can see the separation of the motion of the species, for example, the Hall currents that are in these small regions. In partially ionized plasmas, also in the distances of the ion neutral mean free path, we can see the separation of these species. And here you see just the video of the reconnection, and you see actually on top of the momentum, at the bottom, the electron momentum is the norm of the momentum. And then you see that, for example, you can see shocks in the ions because they are supersonic. In the electrons, you don't see the shocks. They follow the ions, but they are subsonic. And you can see some features that resemble turbulence. Also, I studied reconnection in tokamak, street tokamak. So it's just a screw pinch. So I neglected this curvature, which is important actually. But just to show, this is a kink instability. So I added a small perturbation. And then you can see how it starts kinking. So it's the so-called sawtooth instability. And you can see some reconnection happening. And another thing that is also important, and I will not talk too much because I think Davide will talk about, is drift instability. So in fusion, drift instability is very important actually. And you cannot see it in ideal MHD. And in this case is produced by the gradients of the density, so the diamagnetic current. When you have a small density perturbation, it can produce perturbations in the electric field, and due to the E cross B drift, you have perturbations in this velocity that will create a wave propagating along the azimuthal direction. And this is the simulation with the multifluid. However, indeed, then, and it was interesting to read. It was one of the reviewers of one paper that pointed at Braginsky, that is in the Russian literature is the master of the fluids, right? And then Braginsky, in his paper, actually he mentions the multi-fluid regime at some point, and he says if the collision frequency is low, it's more convenient to use the individual equations of motions of each species, so it's multi-fluid. However, he's a bit reluctant because that actually would invalid some of his results, I believe. And then he says, strictly speaking, the kinetic equation should be used, right? And why is that? Because you see some of the terms of the Braginsky equations, like for example, the parallel conductivity, it becomes infinity, it becomes singular when you are in the collisionless regime, right? So his closure doesn't work, right? And the other difficulty that I will briefly discuss, it's on the numerical approximation of these equations. In my case, with the electromagnetic equations, you have the maximum of your eigenvalues is the speed of light. And actually, it's something that you will never get close because you could require to have relativistic effects. So this imposes constraints that are very, very constraining. Okay, so I will start with the high order moment equations. So how do we derive the high order moment equations? So we start with the Boltzmann equation. So the Boltzmann equation is an equation of evolution for a probability density function in a 6-dimensional phase space. So it's in physical space and in velocity space. Okay, and this streaming operator is really a continuity equation in the phase space, right? And this is here we see the influence of the external forces, which in our case is the electromagnetic field. And on the right-hand side, we have the effects of the collisions. Okay. And the moment equations, I believe most of you know how they are derived. We define this moment M as is basically, we can interpret it as a weak formulation of the kinetic equation. In the end, we are taking averages over the velocity space, so it's like a Galerkin discretization. But we take averages over the infinite R3 velocity space. And usually these moments are, the base of moments is the monomials of the velocity, and they have a tensorial character, right? And then you end up with a moment hierarchy that the first equations are basically the multi-fluid equations, right? And if we continue to higher order moments, we find the heat flux and the kurtosis. I will comment a bit on what it means, the higher order moment. But we find a problem, that is that this term, that is the flux, will depend on the subsequent in the next moment. So this is a problem because we would require to solve an infinite hierarchy. So at some point we need to close and this is the closure problem. We will compare some of them. I will show some results about this comparison. And the second problem is that we have collisions, and in our case it's one of the worst situations. We have non-equilibrium collisions, reactive, multi-species. So even people of combustion, they say, no, but plasmas are too difficult because we are out of equilibrium. We are far from equilibrium, and that makes things a bit more difficult. All right, so talking about closure models. So the first, actually the first person, I didn't put it in this presentation. The first person talking about moments was Maxwell, and he has in his paper, he puts the evolution equation of an average quantity is this, and actually this is the Maxwell transfer equation because he was the first one. But probably the first person that gave a solution for the closure is in a fully non-equilibrium regime. It would be Grad in 49. Even though in his own paper, he already recognizes that it might not work because he was very perfectionist, probably. And so basically, you will express, you impose an ansatz in your distribution function that it's expanded in terms of Hermite polynomials multiplied by, in front by Gaussian, an equilibrium distribution function. So he's inspired in being not too far from equilibrium, okay? And then we perturb it with a polynomial that on top of that, we know it's a complete basis and that it will, indeed is, as Mario was mentioning before, is a spectral, we can interpret it really as a spectral resolution, right, of the, and here we see some convergence. I took a peak distribution for ions, and then I impose different Hermite polynomials, and you see that the convergence is not too fast, let's say. If you are out of equilibrium, the convergence can be a bit difficult, but if you have enough moments, you will get there because it's a complete basis, basically. See if you're continuous, etc. Then probably it was a bit earlier, but the person that gave a bit the formalism is Livermore, is something called maximum entropy. So it's based on also related to the entropy of Boltzmann, and also information theory, the Shannon entropy. So basically here you will assume that your distribution function is the one that, for a given set of moments, is the one that maximizes your entropy, okay? You don't know what it is, but you say, well, the most probable is the one that maximizes the entropy, okay? And it's funny enough because if you take the Taylor expansion of this one, close to equilibrium, you will retrieve Grad. So in this sense, it's also nice. And you can imagine, it's very nonlinear. This is because you need to compute these alpha coefficients from your moments, and you're inside an exponential. So you can imagine it's not very easy to compute. But if you do this optimization problem, you can retrieve the previous distribution with only 5 moments, okay? So n equal 4 is because you count from 0, okay? But as this one gives some problems of, because it's not very nonlinear, the closure and so on. I forgot to mention, the Hermite is almost automatic, because if you are in the right basis, it's almost automatic. And then this quadrature-based moment method is based on a different idea. It's like, to compute these moments, you need to compute integrals. So we will approximate these integrals with Gaussian quadrature. So basically with quadrature points. And indeed, you can assume that this is Dirac distributions. But also you can assume that this quadrature points is a parametrization of something that is not Gaussian. So this is called, in QMOM, the problem is that the acronyms start getting very difficult because it's high QMOM. Okay, I think there is no, yeah. High QMOM stands for hyperbolic QMOM, and EQMOM for extended QMOM. That is with Gaussians, okay? So I'm gonna compare this for ions, okay? considering a moment closure in 1D that considers 5 moments. So we consider mass, momentum, energy, heat flux, and kurtosis. So the heat flux describes the asymmetries of the distribution function in 1D. And the fourth order moment is the kurtosis in the statistics. It means that the population of the tails is very populated, it's heavy tails or compared to a Gaussian, right? And here I express the 5 order moment, the center moment S, as a function of the previous moments. In principle, it depends on 5 moments, right? But by a dimensional analysis, we can see we have 3 independent dimensions, mass, time, and space. So it depends only on 2 non-dimensional parameters that are the non-dimensional, the standardized moments R and Q. And we compare the different closures, grad, Q, high Q mom, EQ mom, and maximum entropy, and we see already something bad happening here. In maximum entropy is that there is something that Jung is a mathematician that discovered that it becomes singular, this closure. And why is that? Is because if we go back to this expression, we see that if the distribution needs to go to 0 at infinity, so the last coefficient needs to be negative, okay? So if the coefficient gets close to 0 or positive, then it blows up. So it's basically that. Okay, so I will compare some results. So we ran some peak simulations in this setup. So it's quite classical. It's just a plasma between 2 walls, and we absorb the charged species on the walls, and we impose the ionization, so we get an equilibrium, okay? And we will only study a simplified model for the collisions, and later we will relax this constraint. And we will impose the ionization from peak. So we will compare directly to peak to see how it compares. Okay, so I go to the results. We run different pressures. So the pressures go from here. I present the inverse of the Knudsen, because sometimes in plasma physics, in low temperature plasma, they refer. So this is a very collisional case, and this is basically here you have 100 collisions per length, and here you have 10 collisions per length, more or less. And you see that actually, in particular, grad and high Q mom, they compare very well. Actually, most of them compare very well. We have problems because of this singularity at low pressures in EQ mom and maximum entropy, okay? However, this was only the density. We can compare the rest of the moments to see if actually we can see inside the sheath, if we capture the structures inside the sheath, and also if eventually we can get the distribution function out of our fluid moment simulations, okay? So we see that actually the temperature is captured rather well, and the first difference is probably is here in the heat flux, right? Like here, the heat flux, already we see that the Fourier law, even at high pressure, doesn't compare very well inside the sheath. And we see that the heat flux is well captured. So the inference of the distribution function. So here is the distribution function computed at different places of this simulation. In the center, near the center, at the sheath edge, and at the wall. So at high pressure in the center is a Gaussian, so basically all of them are able to capture it. But as you get towards the sheath and the electric field is very high due to the charge exchange, you will have a very long tail. And you see that at high pressure, already with a Gaussian, you are not able to capture the distribution at the sheath edge. But you are able to capture very well the sheath distribution with the other. So one thing, just is a detail that I can comment a bit. So there is a way of increasing the number of Diracs in high Q mom. So I don't have too much time to go in this. So that's how I created this distribution out of the quadrature points. Okay. And at intermediate pressures, the things gets a bit interesting because you see that grad, it starts having problems in the tail. In the tail, it gets negative. And the other ones, behave quite well, and at very low pressure. So basically here we have Knudsen equal 10. The one that behaves more robust is really high QMOM. Okay, so in this sense, even the predicted distribution function at different points is rather good. Okay, so now going to more realistic collisions. In the previous case, we were using this distribution, this cross-section that is basically goes as the inverse of the velocity. So basically the collision frequency is constant, so sigma times v is constant. But in this work, we wanted to also compare to the integral of the Boltzmann operator. And to do that, we will compare only the two cases, the anisotropic Gaussian, so a Gaussian that has two temperatures, and QMOM by considering just Dirac's or by considering Dirac's with a transverse temperature that is computed with this moment, okay? And I don't have too much the time to go through the derivation of the operator, but I present here a different example. So it's an example where we have a DC case with a secondary emission. So we have basically a DC discharge. And we see that in this case, it's a bit more challenging for isotropic or anisotropic Gaussians to get the results, because basically you have a very big sheath already. And also you have a higher pressure. So the distribution will be, because of the charge exchange, it will have very long tail. And we see that thanks to this high QMOM with the Maxwellian in the transverse direction, you are able to capture the density. Okay, so I will jump to the electrons very fast. So in the electrons, as I was mentioning before, the operators get a bit more difficult because we have, in principle, in a noble gas, we can have electron-electron collisions, electron-ion collisions, even though we can say that they are not very dominant. Electron-gas collisions, that are probably the dominant ones, right? The inelastic collisions, where the internal energy of the atom changes. And reactive collisions, in this case, is electron impact ionization, okay? So the different operators are the inelastic collisions can be modeled with this Wang-Chang-Uhlenbeck operator. That is very similar to, basically all the operators are a generalization of the Boltzmann operator. But here you just take into account that you lose the energy in the collision. So these primed distributions take into account that you are losing the energy at the collision. And also you can consider the degeneracy of the quantum state if you have, but in most of the cases we are going from the ground to a state that usually we consider that is not degenerate. And well, the ionization collision operator, it gets much more difficult. But usually we do a simplification. So basically we simplify that we don't consider the recombination. So because the ionization degree is so low and it's also a three-body collision. So this is something that it helps. And the second simplification is that usually we consider that the energy of the electron is either 0 or the half of the previous energy. So we kind of treat it as a two-body collision, right? So in the end, it can be treated almost like a Wang-Chang-Uhlenbeck operator. So in this case, I'm going to consider grad. I can, because if you want to start by something, is start with grad. It's the easiest. And the second is because also there is a reason the electrons are usually much hotter. So we can assume that approximating them as a Gaussian can help. If you are not, if you are hot enough that you ionize with enough electrons, because if you are, for example, in this DC discharge where the distribution will be very depleted at the tail, then probably a Gaussian is not a good approximation. So the classical approach is either you can consider that you have electrons that are Maxwellian and gas distributions that are Maxwellian, that or that they are not Maxwellian but they have small drifts. Okay, so small drifts compared to the thermal velocity. So you can tailor expand the distribution around velocity 0, and then you have there is also a paper talking about large drift, general drifts of Benilov at 97. And what I try to do is consider general drifts and also non-equilibriums to see the non-equilibrium cases. Okay, so this is the equations for the 5 moment equations in 3D with 2 contracted moments. So I contracted the heat flux just to have a vector, and I contracted the 4th order moment just to have a scalar. And I'm gonna compute these source terms, okay, for the, okay, so no details, I'm sorry for that. I jumped to the results, but I find interesting new things, even though it's corrections of what we know, okay? So the first interesting thing is that the mobility, so the relaxation frequency of the momentum, for example. Already the momentum, even in Braginski's theory, the momentum relaxation at non-equilibrium, you have a term that takes into account also the thermal diffusion. It's particularly important in electrons. Well, it's particularly important in mixtures where you have a particle that is lighter than the other ones. Okay. And the novelty is that actually these 2 coefficients, because you have a distribution that is anisotropic, that is drifting, they become a tensor. So the frequency, it depends on the direction, right? The relaxation frequency. Even though you see that the corrections is of the order of 10%, okay? So probably the largest influence is the influence of the Mach number. So basically, if you have large drifts, you can change your coefficient. Okay. I put some examples of the results. So you have the same effect in the heat flux equation. Okay. So in this heat flux equation, you have a relaxation that will depend on the velocity, and a relaxation that depends also just, and same thing, they are tensors, and you see the effect of having, for example, a pressure tensor that is not isotropic. Okay, so the most important one is the inelastic collision. So basically what I was mentioning, the kurtosis represents the tails of the distribution. So if you depopulate your tails, you actually will ionize less, right? So this the population is this delta function is variable is basically the excess kurtosis normalized to the standard one. So it's a measure that when you are negative, you are depopulated. Basically, when you are 0, you are a Maxwellian, and when you are positive, you are heavy tails. And you see that there you have orders of magnitude. Basically, you have a huge impact but this is somehow obvious, right? Like depends on your temperature, right? Like probably in Hall thrusters, it depends, right? Like at 5 eV, it becomes less and less important because your tail is populated. It can become important for the second ionization or things like this, right? Some other examples is an effect just with electron-electron collisions, okay? That in this case, we have a coupling between different moments of different tensorial order, which is something different from Braginski, for example. Braginski, they will only couple heat flux and velocity and in the source terms, right? And in this case, you have the coupling also of these terms that depend on the pressure tensor. Right? Okay, so we ran some cases in 0D just to validate this in argon with different reduced fields at different ionization degrees, characteristic of low pressure. And actually, the interesting thing is that you can reconstruct your VDF with the grad. And you can see this depopulation out of your moments, okay? Also compared to the linearized grad, what we see is that at high drifts, the linearized grad starts diverging, okay? Because it's 0D, we don't see the effect of the Knudsen, right? Like in 0D, we can only just put a larger electric field just to see more drift. All right, so some conclusions. Okay. So I didn't talk too much about it. There is challenges to resolve the equations numerically. Okay, and the collisions, even though I showed the results and so on, it took me super long time to do that. So it's an integration in 8 dimensions. So you have in the unit sphere and then the 2 velocity spaces of the 2 particles. For the ions, the conclusions we have in the cases we have run, that hyperbolic high Q mom is quite promising. And in the electron equations, we see novel effects, but we didn't run any 1D case. So actually, it's to be done. So just some, I'm good in time or, okay. So just some problems I had. Is almost a therapy. Some problems with resolving the multi-fluid equations here. Every time I know somebody doing the multi-fluid equations, it's time to discuss because it's true that it's difficult. When these cases of multi-fluid and Maxwell, I had the advantage that is, as it's the chromosphere of the sun, the boundaries are periodic. So in this sense, it seems more difficult because it's Maxwell. But your species have less mass difference, so it's hydrogen. Sometimes you even cheat with the mass ratio, so because it's more interested on the physics. Also, cheating in the speed of light is allowed in this community, but in our community we cannot cheat on the mass of the ions, right? Like, so the approach I took, and it's quite pragmatical, and there is for sure other ways. So it was implicit, fully implicit, which I will give some comments about that. Then I will discuss something about the numerical dissipation because as you have, I will discuss about it, but we actually used some kind of preconditioning for the numerical dissipation. Okay. Also, I will comment some things about the reconstruction. Okay. Okay, so this is the dispersion of waves in the 2 fluid coupled to Maxwell in a homogeneous background. Okay, I find it's quite interesting because here you have at large scales you have the alphenic wave, the fast magnetosonic, slow magnetosonic. Actually, as you get to smaller scales, they degenerate to ion cyclotron, electrocyclotron, ion sound. And the problem is, as you solve for the 2 set of equations for ions, here it would be the ideal MHD, but you solve for the 2 fluids, so you still have this in your set of equations, right? Like the plasma frequency that is too low. And also even you have the electromagnetic waves or the electro sound. So that's a bit showing the disparity of scales you can find, right? Like, all right, so okay, so the ideas about this tackling this disparity of scales is based on the preconditioning. Okay, I will go through it. So basically what we have in the electromagnetic case is that we have the spectral radius of the homogeneous system. So basically, if you take the Jacobian of this F, the maximum eigenvalue is the speed of light. Okay, so you are not even interested about that. So probably you can go to a Darwin approximation. But at the time, it was too late in my thesis to go this way. So okay, so then you have delta t that if you take an explicit discretization that is way too small. You see, I tried to put this diagram. Here the velocity u could have almost not moved anything in 1 delta t. So you would require 1,000 delta t's to just move 1 cell, right? Like, and it has also another problem. It's not, you can say, well, I do it in implicit and then I kill this delta t and then you can advance. However, your numerical dissipation still scales as the speed of your spectral rate, as the speed of sound of light in this case. So your numerical dissipation is too large, is way too large. Even if you go to second order, it's just c times delta x squared. C is still too large, right? So the idea behind that is based on, in Maxwell's equations, is nice because this f is linear. So precondition is quite easy. So the precondition is just multiplying these equations by a matrix that will make your eigenvalues that are very dispersed to make them a bit more comparable, basically. So you are not accurate on these scales, in the scales of the speed of light, but if you don't care about them, eventually you can make a better preconditioner that is, if you have relativistic regions, you can adapt it so they are well conditioned there. So this is just a test case that is basically a wave that we know is a linear wave, even though it's a nonlinear set of equations. We solve the linear wave and we compare to the analytical solution. And then we see that actually the slope by using this preconditioning is able to achieve something similar to second order, even though it's not second order. And if you don't use this preconditioning, basically you get first order at most. Okay, some other hall of horrors of these simulations. This is, well, I thought it was okay, but then I ran this test case with the reconnection, and the only thing I'm changing here is just the limiter, okay? So the scheme is the same. It's just the flux limiter that in principle will act only in shocks. And what happens here that we have an instability that doesn't appear in the other one. So we have different explanations for that, even though I could say it requires a bit more research about that. But the thing is that as here the region starts becoming very sharp and you have many dispersive waves, the thing is that the limiter sometimes gets crazy about these dispersive waves that are not very well resolved. And then basically it's limiting even if it is a wave, okay? So there is some versions of limiters when you have a smooth background and you have waves. So you don't limit. Here is the example of plotting the limiter in a solution when you have shock-shock interactions, turbulence here and so on. And then it limits only around the shocks, but well, you cannot, here when you are under resolved, somehow you get a limiter, but at least it limits only around the shocks. Okay, so if I have some time, the electrostatic solver, which I mentioned before, I have the feeling that it's even more difficult because the mass ratios we are having. So this is the two fluid equations coupled through Poisson equation, okay? And I will just present one 1D case, okay? And we could normalize, I skipped this slide here, but we can normalize the equations and the non-dimensional numbers that appear here that we chose are the mass ratio, so the mass ratio between ions and electron, the temperature ratio, which can play a role, and the normalized Debye length, okay? And all of them are small, actually. So you have a case where you have 3 small numbers. So usually you don't like small numbers in resolving, because it means you have different asymptotic regimes. You have a regime where indeed the electrons are Boltzmann. You have regimes where you are quasi neutral, and you have regimes where you are pressureless ions. Okay, so we chose another type of discretization that is different from fully implicit. It's just making implicit some of the terms. So it's the terms that I call here the ones that are most stiff. So here you're divided by this mass ratio in the normalized equation. So this term is the one that will make your electrons be Boltzmann, right? Like these two terms are of the same order. And you want this to be whole. And also these two terms, you divide by the Debye length here, the normalized one. So it means that Ni is equal to Ni in some regions, right? So by doing this, you can actually remove these two constraints. So basically, your delta t could require to resolve the plasma wave, the electron plasma wave. And by accuracy, you would require to resolve the Debye length. And by taking them implicit, it doesn't mean that you are more precise. It's just if you don't resolve it, at least it will be quasi-neutral. Okay, so it's basically that. If your physics are not quasi-neutral, you should resolve it, right? But if you don't resolve it, at least it doesn't blow up, right? So there is this type of, that is something I didn't know before my postdoc, of schemes that you split the equations into an acoustic system and a transport system. So it's called Lagrange projection, okay? And these equations that seems very bad because it's not conservative, right? But you can write them conservative. If you solve instead of n, you solve for 1 over n, okay? Is the mass variable. So you divide everything by n. And actually, it has also the advantage that is positivity preserving because you solve for the inverse of the density. So it will not, if it gets to 0, it will increase. Okay. So here I resolved something that is a bit very extreme. So it's something that you have a mass ratio. The mass ratio is realistic, but it's just a perturbation that I don't want to resolve the Debye length. Okay. So I have in my domain 10,000 Debye lengths, and I want to put only 100 cells, okay? So this is just a two-stream, I put a two-stream wave, okay? It's not an instability, it's just a wave. So I mean the stable rate. And then in principle, it should propagate, and I know the solution. However, of course, if you have a standard discretization, if you don't resolve the Debye length, it will start moving. Even before the ions move, the electrons already blew up. And here you see that the discretization is able to capture that the wave is quasi-neutral, it doesn't blow up, okay? So these are some, I don't have time to go through the details, but in this acoustic system, the acoustic system is, sorry for that. The acoustic system is very nice in this isothermal case because you have two acoustic waves at the speed of sound. So you can precondition them easily, and then you can reduce this speed of sound. Right? So I use this preconditioning, and you see that if you don't use it, you are still quasi-neutral, but your electron velocity can become very, very inaccurate. And by using this preconditioning, we can say, we can capture better, even though the error in the electron velocity is always very large. It's larger than for the rest. Okay, so here, as we are using this preconditioning, so you remove the problems with the electron speed of sound, and you remove the constraints of the Debye length and electron plasma wave. So you can have CFL numbers that are larger than 1, even though it doesn't cost more than an explicit one. So you can go, I tried up to 28, so CFL 20. And there is limitations of this scheme. So it's only for, it can be extended for higher order moments, but I didn't do yet. And it's first order, but it's really first order. So in this sense, it's first order, but extending it to second order is difficult, okay? So it's not straightforward. But in this kind of cases where you have clearly a very large domain where you are quasi-neutral, it really makes a difference. So just, I put the same case of the plasma between the two walls. I believe this is the last result. And if you don't resolve the Debye length, you can have huge problems with first order HLL scheme. This is a first order HLL. And I wait until the end because it's funny, because then you converge to a very good result. So we need to be careful. Because yeah, I mean, in this case, I know that I'm under-resolved because I'm using 100 cells for 100 Debye lengths. But it's true that sometimes we can under-resolve. All right, so conclusions. It's a very difficult problem with a lot of open questions. But it's very nice, so I'm happy of reading your thesis because it's very nice and you went much farther than what I did. The Through terms are very stiff. I didn't talk about it, but also the collisions can produce problems. The dispersive phenomena, as we saw with the limiter, can produce some weird effects sometimes. And my general conclusion would be it's a specific set of equations, so it might require a specific schemes. So maybe we need to really do specific schemes for coupling to Poisson. Also, specific verification problems that, unfortunately, in the electromagnetic case, there is many. Like you can do the Brio shock tube, and even in the two-fluid case, and there is not analytical solution, but you can compare code to code. But in our case, we have much less verification cases. In the electrostatic case, it's much more difficult. Yeah, so I saw some instability sometimes triggered by the numerical that were, yeah, sometimes it's even something that is not physical, then it becomes physical and then it comes back. The implicit schemes, they showed quite robust, but they were very expensive. So that was a bit my experience. So, sorry. So I'm not sure if I could recommend fully implicit, but it's robust. So, you know, it's over dissipative, but it's stable. The asymptotic preserving schemes are very nice, but well, you need to, for your set of equations, you need to play until you get one, so it takes more time. All right, so thank you very much. I would like to thank also, I think it's my first presentation of the ERC, so I need to thank them. And also all these people that I presented work from many years, so I work with all these people. So thank you very much.
Thank you very much, Alejandro. Very intense presentation.
Yeah, many results. So.
Do you have questions?
Okay, Alejandro. Well, first of all, thank you for the presentation. It's very interesting to have you here, and in a topic that I'm personally very interested. Okay, solving fluid equations. What are the multiple ways we can do them, and so on. I wanted you to elaborate on the Darwin approximation because you mentioned it in passing. So you couldn't consider it while you were doing that work, but would you say now with your knowledge that it is something worth it? You are, I hope, removing the speed of light from the problem. Does it have any drawbacks? Because that's actually something that I'm trying to do. And on our case, at least in the very simple scenario we're simulating, it works pretty well. Okay, but I wonder if going to higher dimensions or in any case that you might have encountered, you could advance that it will be a hurdle to use the Darwin model.
So indeed, like in my case, I think probably because I started from this literature, yeah, that was full Maxwell. So the work of Schumlack and so on. So in this sense, you can apply all the hyperbolic solvers, which is an advantage. But right now, I couldn't do it. Right, like the Darwin approximation can be also computationally expensive in high dimensions, right? But I have less experience. But I think it's, I mean, if you know a set of equations that are describing your physics and the problem of the speed of light is really a paradigm because you are not interested in the speed of light at all, right? It's really, even if you were close to this, you would require to have a different set of equations. So in this sense, I think it's something good to do. Yeah.
Well, that feels encouraging to continue.
Yes. I could say it's the way because I think it's overkilling, right? Like.
Thank you. I don't know if I can ask another question. Yes. So I'm also very interested about the asymptotic preserving techniques that you presented at the end. And I didn't have the time to go through it because, so in what sense it is asymptotic preserving? It's because you are putting the small parameter on the right-hand side and you are doing this implicit? Yeah. This is the reason you call it asymptotic preserving.
Okay. So basically, it's probably a consequence of that. Okay. But basically, when you have the discretized equation, then you tend your parameter to 0. And then instead of blowing up, then you have, in this case, you would have n equal ni. right?
You need a formulation where the
Exactly.
going to zero doesn't blow up the equation.
Exactly. That's exactly.
But it's different from splitting the operator in this way. This is what enables that you have it this way.
So I think you can, and I think there is literature of last year of people that got an asymptotic preserving without doing this splitting. So you probably can get it without the splitting. The advantage here is that by treating, you simplify the problem. You pay because you have a splitting error. So
Right.
It's not you simplify the problem into an acoustic that is much easier. But yeah,
It's a very interesting technique.
It's I'm not there. There is indeed like recently is a work from Di Marco that they investigated the asymptotic preserving without doing, but it's actually quite based on this idea. So we can.
Okay, thank you.
Questions?
Thank you, Alejandro. Very interesting presentation. I really enjoyed it. And I want to ask you one question that maybe I didn't quite understand. Like the main goal of resolving this fluid moment model is because it is in principle simpler than solving the fully kinetic problem, because it's more computationally expensive in principle to solve the fully kinetic model. You have also shown some comparison between your model moment with respect to Fick. So my question is, in order to get a good comparison for a weakly collisional case, so for example for the Knut equal to 10, what is the computational gain of using your model with respect to solving the problem with a kinetic formulation?
So in this case, So actually, it's not a fair comparison because. Here, as I was mentioning, so I imposed the ionization and electric field from Fick, so I'm not solving for that. Because if I solve the full two fluid coupled, I wouldn't know if it's a problem of the closure or a problem of the coupling, right? So that's why I wanted to separate it. So, and the closure, it depends on how many moments you consider. So in this case, Anatole, I just finished the thesis, by the way. So he did a very good job because he went up to 5 order moments, so not very high order, but he did a full analytical description or approximation. So he approximated with interpolation of everything that you require. So the eigenvalues, for example, or the closure itself. So computing this in maximum entropy is very difficult because you require to compute the distribution function at each point here, but you can see that it has a shape and you can approximate it and so on. So in this sense, in this case, the fluid simulations were very, very fast. But I was not solving for the electric field, so I don't have the answer. It's promising, but it depends. If you go to very high order moments, you cannot interpolate anymore. And then probably it gets as difficult and as expensive. So.
Yeah, I understand it's an open question still.
Yes.
Okay. So, and I have another question about the quadrature model that you were showing. It seems that the high Q mom seems to be doing a quite good job. And I want you to elaborate a little bit more on that because I didn't quite understand it. I'm not an expert on this kind of model, but it seems like you're doing something similar to Fick because in the end you're discretizing your velocity distribution function in terms of Dirac deltas. So it makes sense that it resembles better what we do in particle in cells, right?
Yeah, indeed it has. I interpret it also a bit like this with the Diracs that are weighted. So on top of that, you weight it's like having Fick where you weight where your population is more populated. So you have less particles. So in this sense, I interpret it as well like this. The high of the high Q mom, the hyperbolic, is just because you fix one of the deltas, the Diracs, at this velocity. And like this, you guarantee that it's hyperbolic. So numerical is more robust, to be honest. And then you have 5 moments, so you fix one velocity, and then you have 4 other parameters. So that's a bit.
Could you move these as particles?
No.
Characteristic equation for each of the velocities?
Actually, you could, but you solve the moments still. So it's funny. Yeah, you solve still the moments, and then you compute the Diracs. But probably, I assume you can. I mean, it's a bit like in fluid mechanics. You could just change the basis and take the characteristic speed, and I assume that the characteristic speeds are this one, and this one. I'm not 100% sure, but it looks like this. So indeed, if you symmetrize your system and probably you solve for this, but it's, probably the system is not linear or something. But it's a good point, actually. It's something that can be done indeed. Like you symmetrize and you see if your characteristic, your Riemann problem is really, actually in this case, is a pressureless gas moving at 3 different speeds. So.
Thank you. It's a very interesting thing.
Thank you for the question.
Last question. Okay, let's do the last question then. If you compare the fluid method with the particle-inside one, when you go from 1D to 2D, 3D, the difference in computational times, the ratio increases?
Yeah, very good question, and it's open, very open question. Okay, so yeah, so this grad closure is easy to go multi-dimension because it's kind of analytical and you can. However, computing the quadrature is kind of 1D because you can compute quadrature points in 3D, but it's very costly. But there is some new ideas that so going quadrature based in 3D, 3V, it's costly. I cannot say more or less than Fick, right? Because also comparing to Fick is sometimes difficult because the numerical noise is difficult to quantify. So you can do very under-resolved Fick and it's very fast indeed. So yeah, so multi-dimension is open question, I would say. In maximum entropy, there is some closures for 14 moments that are quite fast. So yeah, there is open question.
Okay, thank you, Alejandro. Okay, let's thank our speaker again.